Welcome to our Network Fuzzer demo video. Network Fuzzer is a subcomponent of AI4SIM that focuses on performing rule-based and AI-based attacks against different network protocols, particularly in use case 3 with the DICOM protocol. We extended the fuzzing capabilities of our previous tool, 5G Replay, in Network Fuzzer with 3 core modules. Protocol Traffic Mutator generates mutation rules and adapts its behavior based on real-time server responses. The Integrated Feedback Collector monitors responses, logs, and errors to enable a closed-loop fuzzing process. GAN-based Traffic Generator uses GAN to produce realistic synthetic DICOM traffic, supporting anomaly detection training and the discovery of potential vulnerabilities. Finally, LLM-based Rule Generator leverages large language models trained on DICOM documentation to automatically generate test rules. In this demo, we will show how Network Fuzzer can be used to perform a DICOM extraction attack, a realistic multi-phase intrusion scenario targeting medical imaging servers such as Orthanc via the DICOM protocol. The goal of this attack is to silently extract sensitive patient data and medical images. We assume that the attacker has already gained unauthorized access to the internal network. From there, the attacker can perform reconnaissance, intercept DICOM communications, and launch targeted attacks against a misconfigured server. The scenario consists of 5 main steps. The attack begins with Step 1, Discovery, where the attacker scans the network using tools like Nmap to identify active DICOM endpoints on port 4242. Once a server is found, the attacker proceeds to Step 2, called AET Brute Force. In this phase, Network Fuzzer is used to send repeated A-associate RQ packets with different called AET values in an attempt to establish a valid session. After discovering a valid called AET and successfully establishing a session, the attack moves to Step 3, Patient Metadata Enumeration. Here, Network Fuzzer sends crafted cfind queries to the Orthanc server to retrieve sensitive metadata, including patient names, study dates, and unique identifiers such as the study instance UID. In Step 4, DICOM file extraction, the attacker uses these identifiers to send CMove requests and download DICOM images, which may then be analyzed, modified, or exfiltrated in Step 5. Optional analysis for malicious purposes. Here is our simulated environment for the DICOM protocol testing scenario. On the left, a client machine runs the DICOM simulation along with Network Fuzzer to generate and inject test traffic, including potential attack scenarios. On the right, a server machine hosts Orthanc, deployed as a service to process and respond to DICOM requests. Additionally, the MMT security monitoring framework is installed on the server to perform packet sniffing and traffic analysis. In Step 2, it iterates over plausible, called AET values, by modifying normal traffic and crafting minimal, valid A-associate RQ packets. Each response is analyzed. An A-associate accept confirms a valid called AET, while a rejection or a warning in the server logs triggers further refinement. In Step 3, we use the LLM-based Rule Generator to create a rule for modifying the patient name field in P data packets. A new rule with ID 47 is generated in XML format, compiled and used by Network Fuzzer. Network Fuzzer then takes advantage of the DICOM cfind service by gradually fuzzing the patient name field, starting with a single question mark, then 2 question marks, and so on, to infer the length of valid names. Once the length is identified, it brute forces the initial characters and analyzes server response sizes. A 154-byte response with 100 bytes of payload indicates no match, while larger responses suggest valid entries. Eventually, a valid patient name of length 9 starting with R is found. Using the extracted metadata from the server's responses, we proceed to retrieve the corresponding DICOM images. Thank you for your listening.